Welcome everybody, and thanks for having me at this virtual version of the RISC-V Summit 2020. My name is Florian, and I am the Open Hardware Director for the Hardware and Software Task Groups. And today I have the pleasure to present to you the Core 5 MCU SoC, which is an open source MCU in 22 nanometers with an embedded eFPGA from QuickLogic. So before we start things out, let's touch a bit of history of the Core 5 MCU. So both platforms, I'm saying both here because the MCU and the application class processor originate from the PULP project. And the PULP project is a project led by Luca Benini of ETH Zurich, which I'm a PhD student at as well. And our goal is to really make systems which are tuned for a very, very high energy efficiency. So this is our primary goal. And we achieve this energy efficiency with custom ISA extensions and various other techniques. So the Core 5 MCU is actually derived from the Pulpissimo framework. And the Pulpissimo is an open source single core system from the PULP project, as the name gives away. This is a very efficient microcontroller. And we have taken the Pulpissimo and swapped out the RISC-V core with an improved version of the RISC-V core, which got the new name CV32 E40P. So the P stands for PULP because it has all the PULP extensions. And we have swapped that out. We have improved RISC-V and made it the CV32. And we also improved the on-chip interconnect, which is now a standardized open bus interface protocol. The standard is within the Open Hardware group and has been contributed from one of our member companies. And one thing where we also gain efficiency is on the I/O subsystem, which is controlled by the micro DMA. This is a very small DMA which can autonomously move data from the I/Os, and it's controlled by the APB. And although this talk will focus on the MCU, I will also briefly touch upon the APU, which is derived from Ariane, which is now a CVS6 and within an open hardware group as well. This one is the Unix capable, so an OS capable core with a very minimal infrastructure to demonstrate the core. So the Core 5 MCU consists of the CV32 E40P. It has a tightly coupled data memory interconnect and a shared memory. And with this interconnect, there's a unified data and instruction memory partitioned into multiple banks, giving quite high throughput to access by the core or your custom accelerator. So the custom accelerator is actually quite a neat feature here. It is so the interconnect gives the opportunity for custom logic to actually get quite high data bandwidth into this shared memory hierarchy, and the APB interface makes your custom accelerator controllable via the Core 5 core. The microDMA is the efficient I/O subsystem. It can autonomously copy data from and to I/O from the tightly coupled data memory as well. And so the MCU is really meant to be used in kind of a larger system where you want to have your own framework and kind of having a ready solution where you can plug your own custom accelerator. The I/O subsystem is quite rich. We have a UART, we have a quad SPI for like quite high bandwidth data movement from SPI flash. We have a camera interface, mainly like for vision and so that you can run your AI algorithms on images. We have an I2S and an I2C for audio and just sideband traffic. We have JTAG, GPIOs, and an interrupt controller. The custom accelerators gives you quite a neat, ready-to-go framework where you can plug your own accelerator and your own secret sauce, which makes the system like really efficient and nice to use for your use case. So briefly touching on the interrupt controller, it's a little bit special. It has the notion of events, and events are different to interrupts in the sense that they do not detect redirect control flow, but they just like set a flag and they can wake up the core from a deeper sleep state. The interrupt controller is mapped to the APB, bus as well, and it has a FIFO where it can receive events from the rest of the SoC, common sources being timers, GPIO, or your custom accelerators. It has the usual kind of registers for masking, pending interrupts, acknowledging, and so on. But in addition to the interrupt controller, our improved CV32E40P also has support for the RISC-V fast interrupts, which is quasi-standardized as it's not ratified yet, but we already have support. So let us shine some more light on the custom accelerator side. The custom accelerator, this is really a nice thing of this platform because, as I said, on the left-hand side of this binary neural network example, which really meant as an example in that case, you have 4 ports into the TCDM. This gives you quite a high bandwidth where you can fetch input sources, weights, or you can write back the output. And on the top, you can see the control port of the accelerator, which consists of register, like a control and status register file, or some microcode where you have like the control of FSM stepping through the microcode and doing the thing of the accelerator. So the Core 5 MCU comes in 2 realizations. One is the FPGA design. We currently support the Nexus A7 from Digiland, as well as the Genesis 2 from Digiland. And the second realization is an ASIC, which we are going to fabricate in 22 nanometers global foundries, hopefully at the beginning of next year, including a QuickLogic eFPGA sponsored by our member company, QuickLogic. And we also want to bring boards to the market in a limited fashion so that you can start prototyping. And so just to give you a notion how this is useful, imagine you prototyping your own custom accelerator for your AI or ML applications. You're going to do so, and you test this on the FPGA, so on the Genesis 2 board. You have plenty of opportunities to refine, test, and so on. But even if the eFPGA version, so the ASIC version comes out, you have the opportunity to have the same framework, the same Core 5 MCU framework, but you can put your own custom accelerators within the eFPGA fabric of the Core 5 MCU. So within the Open Hardware Group, we have this big, hairy, audacious goal, the BHAG. So we have 2 goals here. One is an application class processor SoC, and one is the microcontroller class SoC in a deep submicron technology. So in that case, we are targeting 22 nanometers global foundries silicon on insulator technology. For the application class processor, we are going to take our CVA6 core, which is able to boot an operating system such as Linux. And for the microcontroller class platform, we are going to take CVE4, which is able to boot like a more embedded operating system such as FreeRTOS. The tape out of the Core 5 MCU, so this is like our first goal we want to realize, is going to be the first quarter of 2021. So why can we be so sure that we actually get something running until then? Because we already have experience and we already had made a test chip called the Arnold chip, which is depicted on the left, the floor plan. And this already features an eFPGA by QuickLogic, which takes up quite a fairly big amount of die area so that it features enough lookup tables for your custom accelerator. So the eFPGA itself lives in its own clock domain, can be individually clocked by an FLL, and it has a port into the event unit, as well as the accelerator interface, as well as being able to be programmed by the onboard RISC-V core of the MCU platform. In case you should be interested in further details, we have published a small paper about the Arnold test chip, which I've put the link on the slide. It has this RISC-V core, which is still the RISC-V core. So prior to the enhancement we have done at Open Hardware, we have 512 kilobytes of on-chip memory. So this is quite some memory you can use there. We have this broad set of peripherals I've been introducing so far, accessible via this very energy efficient micro DMA subsystem. The tightly coupled eFPGA has direct connection towards the primary I/O, as well as a shared memory accelerator interface I've been introducing previously. So it can intake quite a lot of data, and it can sustain quite a lot of bandwidth into the shared memory. It also features some I/O filtering functions, as well as this config and control interface to and from the system. So the benefits are multifold, actually. So on the one hand, this can be quite energy efficient architecture because you can put your custom accelerator onto the eFPGA and be more efficient than a custom software solution. And it allows you to be quite agile on the architecture side, because you are able to adjust the architecture, you can do bug fixes, and this tremendously lowers the NRE costs comparing to like spinning an ASIC for each bug fix or derivation you're doing. It allows for on-device hardware upgrades, so you can upgrade your accelerator, you can reprogram it, and it is a better solution than a discrete microcontroller attached to a discrete FPGA. It reduces energy efficiency. It is a better solution and has lower unit costs than a discrete MCU and a discrete FPGA implementation talking over a PCB. So we have announced the project at the OSD forum in September 2020. Go check this out. The talks are all available. We are working on a real-time operating system, FreeR2S, which is capable of running up to 600 megahertz on the MCU with this embedded eFPGA fabric by QuickLogic, with all the periphery we have been talking so far in 22 global foundries silicon non-insulator technology. So that was the hardware, but the hardware alone isn't super useful because we're also providing software, and we're gonna need software. What we provide is an SDK, which contains all the tools and runtime, which is necessary to support our Core 5 based microcontrollers. As a bare minimum, this is a hardware abstraction layer and a minimum C runtime with a linker script and some high-level functions and a standardized API. And we are also shipping and developing and providing our own Core 5 toolchain, which features support for our custom ISA extensions, which makes the thing really energy efficient and which brings out all the power of the Core 5 MCU. If you're interested, I've put up the link to our Core 5 software repository, which contains the roadmap and the project charter of the Core 5 software task groups. And I really want to emphasize this. This is not a single person effort, but this is really like driven by our member companies. And if you're interested, please get involved, get in touch with us, have a look, and yeah, contact us. So what is the current status of the Core 5 MCU? So it is running on the Genesis 2 with a kind of a simple runtime at the moment. The code is already built with our own Core 5 toolchain, which is being built and provided by Embecosm. We have GDB and OpenOCD debug running, and you can join us and contribute and take a look at the RTL in the Core 5 MCU repository. Furthermore, I want to emphasize that the Core 5 MCU is being debugged or being debuggable also with the debug probes of our member companies and the IDs of our member companies, such as the Ashling RISC-V with the Opella XD JTAG probe, all on the Genesis 2 board at the moment. So next steps involve further testing and debugging of the implementation. And this is really one of the core features of open hardware and what we are going to provide. So we really want to take RTL, which has been written in kind of an academic setting, and we want to bring it to an industry level assurance quality. And Mike, my colleague, is going to have an in-depth talk and workshop on what we are doing on the verification front, because this is really the main benefit the open hardware group brings to the existing systems. We are planning on integrating more system peripherals and advancing and enhancing our SDK, as well as architectural enhancements, such as implementing the open bus interface, which CV32 now supports and which has been contributed by one of our member companies. Validation and integration of our proprietary open source tools, both on the hardware and the software side, which is driven by our member companies. This is an integral step. And finally, and I think this is last but not least in that sense, we want to make sure that there are enough training materials, documentation, and demonstrations available, so to get you like easily started and to get more people on board of the open hardware and RISC-V train. So if anything sparked your interest so far, we are always looking for collaborators, and we're happy for you to get on board. As briefly mentioned in the introduction, we have a second set of system, which is the Core 5 APU, the application class unit, which features our CVA6 core, which is it's an application class core, and it has a very small dedicated SoC built around it, which is meant to showcase a Linux boot. And so we don't have like anything fancy around it, but the main UI is really a UART. We have a zero-stage bootloader, which is burnt into LUTROM. We are fetching Linux from the SD card, and we have a couple of gigabytes DDR attached, as well as some Ethernet for like network connectivity, so that the system is kind of useful, and people can take a look at how this is composed. So both the MCU and the APU are targeted for FPGA, kind of in an emulation context. The default board being for both platforms the Genesis 2, mainly because it's quite widespread. It has a lot of peripherals and a lot of IOs and interesting peripherals, and it is reasonably cheap. So we have discounts for open hardware, and academics also get a discount. So be sure to check that out. For a cheaper alternative, only for the MCU platform, we also support the Nexus A7, which has a little bit higher availability and is, as said, is cheaper. One thing I really enjoy is those user ports. So we have users who don't have the other two ports available, and so they decide to contribute like their own ports. And we have support for the VC707 or the KC705 from Xilinx, and a couple of ultra-scale ports. For both the MCU and the APU, we have support for the official RISC-V debug specification, currently in 0.13. This defines a couple of debug registers, and it allows for running, single stepping, halting the hearts, reading GPRs, floating point registers, or control and status registers, as well as varying the heart status. It is being interfaced via a standard JTAG interface with an OpenOCD software support, which is kind of the shim between the debug probe and the host computer. And for example, we support different debug adapters, one being the probe by Ashling, which is depicted here. And we are also currently heavily working within the software task group on IDE integration to make development easier and more lightweight. So yeah, there's some more details on the debug side. There's a special debug mode. As I said, you can single step and halting and so on. And if you're interested, like, the nitty-gritty details, go check out the system work reference implementation, which we are using, which currently still is within the Pulp platform group, but is being used by multiple users. And so this can also be useful standalone, even if you are not using the microcontroller or the APU platform. So as I said, this is definitely not a single person effort. On the contrary, this is driven by our member companies. And so I have the pleasure of being the director of both the hardware and the software task group. The hardware task group is being chaired by you from CMC and co-chaired by Tim from QuickLogic. And on the software side, we are in the capable hands of Jeremy from Embecosm and Yunhai from Alibaba. So the last thing which remains is development is in the open. It's an exciting time. It is useful. This can be useful for everybody. If you're interested, have any questions, don't hesitate to contact us and get in touch with us. However you like, email or the issue tracker, or join Open Hardware Group. The code is on GitHub, currently hosted on I've put the links there on the Core 5 MCU repository, as well as the APU. The APU is hosted directly in the Cores repository, so go check out the CVA6 repository. So that concludes it from my side. Thank you for your attention. And the last thing that remains is to make you aware of our open hardware booth here at the Virtual RISC-V Summit, where we have prepared some nice demos from you by our partners, CMC, Imperos, Metrix, OneSpin, and QuickLogic.